Okay, so the topic that I want to talk to all of you today about is relating to fuel forecasting and some of the applications that it has for the purposes of mine planning. I'm going to start off by talking about some of the most common ways that fuel forecasting is currently used on mine sites, and then I want to dig into some of the ways that we can look to improve that by using data that we capture. So I'm going to be talking about three different kinds of approaches that we can take towards that goal. And throughout, I also want to be providing some examples to illustrate some of the to illustrate some of the applications that this has to both small and large scale mine planning decisions. Before I do any of that, though, I want to start by telling you who I am and why you should care about anything that I have to say. So I'm David. I'm the lead data scientist here at Cascadia Scientific. I've been in that role for the past 3 years, and during that time, my main focus has been on analyzing fuel consumption data in order to identify new ways that we can drive efficiencies on mine sites. So that's the why. I mean, the who. Now for the why. So the reason that this presentation should be of any interest to you is that fuel forecasting can be used to answer a number of fairly important questions about your site. So the most common one that we see is around budgeting. If you understand more about how much fuel you're going to be burning in the next month, quarter, year, etc., then you have a much better understanding of how much you need to set aside for budgeting purposes for that fuel. But you can also answer a number of other operational optimization questions. So for instance, if you have a non-homogeneous haul route and non-homogeneous fleet, which kind of truck would be best suited to which haul route on your site? And likewise, you can also answer questions about the specific design of particular elements of your site. So you can determine how much exactly particular choices are costing you in terms of fuel consumption. You can also answer some more esoteric questions like, is it worth setting a speed limit on my site? Would that have some benefits for fuel consumption? And what would the corresponding drawbacks be from a productivity standpoint? So I'm going to look at all of these questions throughout this talk, but I want to start off by talking about the first one, budgeting. And I'm going to start by talking about exactly how this is usually done. So this isn't by any means universal, but the most common way that we've seen fuel forecasting used for budgeting purposes is through a technique known as effective flat hauls. So a lot of people on this call are probably going to be familiar with this already, but for those of you who aren't, I want to give a very brief introduction. So an effective flat haul is basically in order to compute it, you start off by taking the block model for your mine, and you decide which of those blocks you're planning on extracting, mining, etc. in the next month, quarter, whatever time period. And then, since you know where those blocks are and you know where you want them to end up going, then you can draw a series of haul routes out from the source to the destination. For each of those haul routes, you can then look at all of the uphill segments of that travel, and you assume a fixed speed of traversal. Then you calculate the time that it would take to traverse it based on that speed, and from that time, you can calculate an equivalent distance the truck would have been able to travel if it had been traveling on flat ground instead, hence effective flat haul. In order to convert that into a number for fuel consumption, there's one final step that you need to take, which is to multiply that flat haul distance by an efficiency metric, usually in terms of like a mileage, so the liters that you can expect to consume per kilometer of travel. Now, there's a couple of different problems with that approach. The main one being that it relies on a number of assumptions. It assumes that your grade is relatively uniform on your site, which is very rarely the case. It also doesn't really take into account fluctuations in payload. So if you happen to be mining in an area with a less dense material, then your trucks are likely going to be traversing up the ramp much faster, which means that your estimates for the effective flat haul distance and hence your fuel consumption are going to be higher than reality would reflect. So how can we improve on that? So the approach that we take at Cascadia is that we capture data related to individual Hall cycles. So we capture data related not only to fuel, but also to the distances traveled, the total runtime, the vertical travel over the time, the payload, etc. And we use all of that to characterize the Hall cycles by feeding that into a model. Once we've got that model, we can then interrogate it to ask it, how much fuel would I expect to burn for each of the hypothetical Hall cycles that I'm going to be expecting over the next month or quarter, etc. But there's no reason that you have to stop at the Hall cycle level. You can also break things down even further. So if you look at an individual Hall route and you sample at regular intervals along it, then what you get is that the numbers for the data that you're collecting don't characterize the Hall cycle anymore. They characterize individual segments along it. And once you've collected enough data about these segments, then you can start to build some pretty useful statistics around them. So in this example here, what you can see is that we've got two different models of haul trucks that have been operating at this mine. And for one of them, the blue one specifically, both the traversal speed and the fuel efficiency is much better when traveling downhill. The green one, by contrast, is much more fuel efficient and travels much faster going uphill. So what that tells you automatically is that if you're operating a downhill haul, then you're better off using the blue truck, whereas if you're operating an uphill haul, then you're better off using the green truck. So that can, if you have a site which has both, then you know which model of truck to assign to which. And alternatively, if you are operating an open cut mine versus a mountaintop removal mine, then you know which truck is best to procure. You can also start to see some pretty useful insights and patterns in the data just by visualizing it. So I've got 3 examples here which show where fuel intensity is most, intense on site. So the first example relates to a non-uniformly graded section of the road. So there are 2 pretty distinct peaks in fuel consumption, illustrated in red in this diagram on the top left. And those relate to areas of the route which are at a much steeper grade than the surrounding region. The second example is a switchback turn. And you can see that fuel intensity is much more intense around the corner where the trucks have to slow down in order to navigate it. Likewise, the bottom example is of an intersection where once again trucks have to slow down almost to a stop before accelerating again. And I don't think any of those patterns come as a surprise to anybody on this call. It makes sense that if the grade is steeper at particular parts of your mine, then you're going to be consuming more fuel when you're traversing them. And it also makes sense that if trucks have to slow down, then they're going to have to burn more fuel in order to speed up again. But what this kind of visualization and this analytics helps you to do is it can tell you how much that's costing you, how much extra fuel you're burning as a result of these features in your mine. It can also tell you what the impact of some of the larger scale changes to your mine would be. So, for instance, if you're considering building a new route or a new ramp, then this kind of analytics can tell you how much fuel you would expect it to save. And you can compare that against the budget that you have for actually constructing the route to see whether or not it makes economic sense. So all of the examples that I've been showing so far have been relating to predictions that you can make based on current operations. But if you want to change something in a way that the mine has never seen before, then the best approach is to combine the 2 methods that I've talked about so far. So if you take, once again, each of those segments, which we have characterized in terms of distance traveled, vertical travel, etc., then instead of just calculating statistics for them, you can feed them into a model like we did with haul cycles before, except now what you get out of it is a model which can be interrogated in order to examine the impact of making changes to those individual segments, which means that you can answer questions related to changes at a much smaller scale, and also answer questions related to conditions which you haven't seen on site before. So a good example of that is in terms of speed limit optimization. So this isn't going to be applicable to a lot of people, because at some mines, introducing a speed limit wouldn't make any sense. But a lot of people have this conception that there's a trade-off between fuel efficiency and productivity, which makes some intuitive sense. Because if you consider speeding trucks up, then as they get faster, they're going to be experiencing more air resistance, which means that you can expect them to be burning more fuel to overcome that. So you might think that by increasing the speed, then you're going to be increasing fuel consumption, but also increasing productivity. What we see, though, like when we do this kind of analytics, is that by introducing a speed limit, not only do you increase the time it takes to complete a cycle, but you also typically increase the consumption that's associated with it. And the reason behind that can be seen if you break down the haul route into components related to downhill travel, uphill travel, and travel on flat ground. So this is data produced with a few simulations for one of the sites that we operate at. And what you can see is that during the downhill travel, if you introduce a speed limit, then you're not really going to be reducing the consumption rate very much. But what you will be doing is increasing the time that it takes the truck to actually traverse that route, which means that the engine's going to be on for longer, which means that you're going to be burning more fuel as a result of it. For uphill travel, things are a little bit different in the sense that once you're actually on the ramp, the speed limit typically doesn't affect your traversal time in any way. You're usually traveling much slower, just by virtue of the fact that you're traveling uphill with, say, 200 or 400 tons in your dump body. But what it does affect is the segments of the route that are leading up to the ramp. So if you are traveling at a slower pace on the flat ground before the ramp, that means you're going to be carrying less momentum into the ramp, which means that you're going to be slowing down quicker, you're going to be spending more time on the ramp, and once again, you're going to be consuming more fuel. We do see that on flat segments of road, there are some benefits to having a speed limit. And if your mine is completely flat, then there may be some case for considering it. But for any practical mine where there's any sort of resemblance of a ramp, then the amount of extra fuel consumed while going up or down the ramp when you introduce a speed limit well and truly outweighs the amount saved when you're on flat ground. By way of a conclusion, I hope I've demonstrated a few different ways that data science can be used to improve fuel forecasting, both from a budgeting perspective, but then also in terms of informing both small and large-scale changes to the mine. I've also talked a little bit about some operational changes that fuel consumption data can help inform. But I'd like to emphasize, as Ali was pointing out during his Q&A time, that all of this analytics relies on having access to both highly accurate and frequently sampled data. Your models and your predictions are only going to be as good as the data that gets fed into them. It also relies on having access to the correct tools to make any sense out of it. And if you want to learn more about the tools that I've been demonstrating throughout this talk, then I'd invite you to stick around for our next speaker, Nicholas Dembeck, who's going to be giving you a walkthrough of both the machine learning and the heat map tools, which I use to produce a lot of the analytics that were shown in these slides.
Thanks, David. If you wouldn't mind sticking around for a few questions we have. So the first one is from Leonardo. Does your model predict queuing time based on distance and truck allocation, i.e. number of trucks on one loader?
It doesn't predict queuing time, but that is something that we collect in our data. So we'd have separate tools which we use to analyze queuing time and inform truck fleet allocation in that way, because like we can geofence, like the data that we collect allows us to geofence all of the activity around like your load sites, which can tell you how long you've been queuing pretty close to real time. And then you can use that, if you see a steady increase in that, you can use that to inform your fleet management team that that a site might be overtrucked.
Awesome, thanks. The next one from Madi. Doesn't each downhill move eventually need an uphill move? So I imagine this is for planning.
That's absolutely true, yes.
Yeah, okay. James asks, when you use the different kinds of modeling and analysis, when would you use the different kinds of modeling analysis? So road segment versus the others.
Yeah, okay. So for the purposes of predicting large-scale operational changes, we tend to prefer to use the whole cycle modeling, because that provides the advantage of that approach is that you can incorporate more variables into it, which means that your predictions tend to be a little bit more accurate. If you want to consider the changes to specific segments of the route, or like to modifications, then we usually approach it using a statistical approach, unless there is good reason to believe that the data that's been captured so far doesn't well represent the conditions that you're trying to model for. In which case we use the segment modeling that I was talking about in the final few slides.
Awesome. So Darren asks, for speed limit example, have you looked at whether imposed speed limit could reduce truck bunching in a mixed fleet and thus have effects on productivity slash fuel consumption? I know we've gotten that before, David. So what do you think?
We haven't looked into that specifically, but that is a very valid point, and I suspect that you're quite correct. The only instance in which I think that it's going to be applicable, though, is that it will. So bunching mostly occurs when you're traversing up the ramp, and it's sort of a result of it's most commonly caused by unevenly loading dump bodies. So if you have a truck which has a much lighter load in its dump body, then it's quite easy for it to catch up when it's climbing up the ramp, because it can just maintain a higher speed on the ramp. Which means that if you are introducing a speed limit to prevent that, then like one of the most common side effects is that you will be increasing fuel consumption as a result, because you're sort of forcing the trucks to spend more time on the ramp.
Great. I hope that answered the question. That's all the questions I have, David.